Now, it's my great pleasure to welcome today Maël Godard from ENSTA in Brest in France to our online seminar on interval methods in control engineering. And he will give a presentation today on enclosing of the image of a sphere by a nonlinear function using parallelepipeds. And Maël, the floor is yours.
Thank you, Andreas, for the introduction. Hello, everyone. So today, as Andreas said, I will talk about parallelipipeds and how we can use them to enclose the image of a sphere by a nonlinear function. So this is a work that I've been conducting during my PhD thesis with Luc Cholin and Damien Massé. So for today's presentation, I will start with a small introduction, a bit about the motivations of this work. Then we'll talk about the parallelepipedic approximation itself. We will see two applications in two dimensions first. One to compute the image of the unit circle, and one to about the integration of an ODE. And finally, we'll see an application in three dimensions, so the image of the unit sphere, and we'll see some perspectives. As Andreas said, I am a robotician. So this is a robot I'm working with. It's called Helios. It's a boat. And the question that I'm trying to answer is the following. I have my robot here in gray, and my robot is navigating blindly from a point, and I want my robot to reach an area here in green where I know that the robot will be able to locate itself. The problem that I have is that my robot is not perfect. There may be some perturbations during its mission. So before the mission starts, I'm not able to say exactly which trajectory my robot will take. And so I need to be able to characterize all these possible trajectories before the mission to be sure that I will never lose my robot. To do this, I need to perform a reachability analysis. To define reachability, I first need to define a flow function. So my robot is a dynamical system. It's defined here by an equation of the form x dot equal f that depends on x, the state of my robot, and u represents all the inputs on my robot, so the motors, the perturbations. And the flow function is the solution of this ODE, meaning that at every time t, my flow function phi evaluated at t gives me the state of my robot at time t. These definitions, I can use it to define the reachable set at a point in time. So once again, if I consider a dynamical system, the reachable set is a set of all position states that my robot can end up in after a time t, depending on its initial state and all the inputs possible. So to characterize this reachable set that I need, the literature, sorry, gives me an ODE here. So I will not go too much into the details here. The reference of the article from Thomas Liu about this ODE is at the end of the slides. But what it says is that if I integrate this ODE for all initial states on the boundary of XO, XO being my initial set, I get the reachable set. To illustrate a bit the principle, say that I have here my initial set XO. I take one initial state here, X at 0. This state has an adjoint state Q here, and I integrate this ODE for these initial conditions for time t, and I get here x at time t. I do this for every point of the boundary, and I get here in gray the reachable set at time t. So this method relies on the fact that I'm able to take all the points on the boundary of XO. Using interval analysis tools, what we can do here on the left is take boxes that cover the unit circle or the initial set. The issue that we have with this is the wrapping effect It's the fact that if I cover my circle with boxes, it won't be perfect. There will be some pessimism here that we can see. And this pessimism, if I integrate an ODE, this pessimism will grow with time, and at some point it may explode, and I may have really big boxes at the end of my integration. And so the idea that we had at this point was that maybe, as you can see on the right, we can use parallelepipeds to fit best to the unit circle or to the shape of the boundary to limit this pessimism and to have a more precise idea of the reachable set. Because in the end, what we want to be able to characterize the inside and the outside of the set. And so the thinner the boundary, the easier it will be for us to determine this. And so here I displayed it in 2 dimensions, but in 3 dimensions, it's even more important. So for the notation that I will use for this presentation, the studied function, I say it must be at least C1, so continuous, and this derivative must be continuous too. I will not Sn the unit sphere of dimension n, so S1 the unit circle and S2 the unit sphere. And we will limit for this presentation our study to the ODEs that can be described like this. So x dot equals gamma x, so there is no input here. Now, for the parallelepipedic approximation, that is the main topic of this presentation, I first need to define what is a parallelepiped. So a parallelepiped is defined by 2 things. Its center, here if I note angle y my parallelepiped, its center is y bar, and a matrix A that contains the vector of that describe my parallelepiped. Here, in 2 dimensions, my matrix A is a 2 by 2 matrix, and it's composed of the 2 vectors A1 and A2. So this is the representation that we will use for this representation. What we want to find and what we need to find, we need to find a parallelepipedic inclusion function. So this parallelepipedic inclusion function is an inclusion function, meaning that if I take a box X, the parallelepipedic inclusion of the image of this box contains the real, let's say, image of the box by the function f. And of course, this inclusion is a parallelepiped. If I show it, if I consider here on the left a box, in this case an interval x, its image by the function f is here in blue, and the parallelepipedic inclusion here is in green. So this is what we want to characterize. We want to be able to characterize and to find a parallelepipedic inclusion function. To do so, we will rely on a theorem here. If I consider a box X and its center X bar, I defined a linear approximation here, Lx. So it's a first order approximation of my function around the center of the box X bar here. And what this theorem says is that I'm able to find a maximum rho, a maximum to the distance between the real function fx and the linear approximation Lx. And so the expression of this maximum is here. It can I won't do the proof here, but it from the expression of Lx and fx we can find this pretty easily. If I show it here on the abscissa, you have x, and on the ordinates you have fx, or n, so the dimension of fx. Here, if I take the center of my box x bar, I do a linear approximation here in red, and rho, the maximum error that is made, is here. And so if I inflate my linear approximation with rho, I enclose the image of my box by f. what will be useful for us is the theorem, but most importantly, the corollary of this theorem. So if I consider once again a function f and the box x, then I can say that the image of my box x by the function f is included in the Minkowski sum of my linear approximation evaluated on the box plus rho u being the unit sphere, and rho being the error, the maximum error that I characterized earlier. Once again, if I show it, here I still have my box x in blue. Here you see in blue f of this box. I take the center here, x bar. I have my linear approximation. Here it's the red line. And the circle that you can see in pink is rho u, so a disk of radius rho. And the Minkowski sum of these two is the whole area here in pink. And as we can see, the blue curve, so the real image, is contained in this set. So what we want to do, we are working with parallelepiped. We want to find a parallelepiped that encloses, that contains this pink set. To do so, the idea here is represented in 2 dimensions. I have my linear approximation. In 2 dimensions, it's a segment. It's described by a center and one vector. I take a parallelepiped enclosing my rho u, so my disk of radius rho, and I compute the Minkowski sum of these two sets. So thanks to this, so the corollary, I can characterize my parallelepipedic inclusion function as follows. So it's defined by its center y bar being f evaluated in the middle of the box, and the matrix A being, well, my flat parallelepiped here, A0, inflated by our rho, so our maximum error made by the linear approximation. And this is what we will use for the rest of the presentation to be able to get the parallelepipedic inclusion. If we take first a small example, if we want to be able to enclose the unit circle, well, the idea that we have is that we can use 4 maps here to be able to describe the unit circle. So we will first work on the red one here, so the first map. And we can, with our parallelepipedic inclusion, we can compute the image of an interval by a nonlinear function. So here I take the interval -1, 1, and the function that I will consider is the function c0 here. So it corresponds to a quarter of the unit circle. This function, I can describe its Jacobian matrix here. And with these two informations, I'm able to construct, with the method that I presented earlier, to construct a parallelepipedic inclusion. I can either here take the whole interval -1, 1 in one single as one single interval, and I get here the result. Or I can subdivide this interval into 4, 10, or 20 intervals. And as I subdivide, my inflation here, as you can see, rho, gets smaller and smaller. And in the end, we can see that we have something that looks a lot like a quarter of the unit circle. And it's pretty thin. Now that I have 1/4, I can construct the whole unit circle by relying on symmetries. Here, if I defined S1 being a rotation of, let's say, 90 degrees, or pi over 2, well, I can define my unit circle with 4 symmetries and the psi0 function defined earlier. So the four symmetries here, we have them. So I start with my map here, my interval -1, 1. The image of this interval by the function psi0 is here in red. It's the result that we had earlier. If I apply once my rotation, I get the blue. I apply it a second time, I get the green. And if I apply the inverse, I get the yellow. So I've been able, with my parallelepipedic inclusion function, and with four symmetries, I was able to enclose here the unit circle. Now we can go a bit further, and we can use this to enclose the image of this unit circle by a function. To do so, if my unit circle here is S1, so I want to compute f of S1. Well, it will be the union of the GI functions on the -1, 1. And these GI functions are defined here. They are the composition of f, sigma I, and psi0. For graphical purposes, here, I will use the anon map that is defined here. So if I go back to the example I had earlier, to the figure I had earlier, I have here my interval -1, 1. The image of this by psi0 is the top quarter of the unit circle. I can rotate this quarter circle with sigma, with a symmetry here to get the blue quarter. And the image of this quarter by f is here. And so my GI function is the composition of these three. And so from -1, 1, the GI function will give me a quarter here of the image. And with my parallelepipeds, it's the same, except I have a non-closure here of the image. So this is a result that we can get for the four GI functions. So if GI has a color, on the left we have the natural evaluation. In the middle we have the centered one. And on the right you have the parallelepipeds. So for the centered evaluations, I didn't talk much about it because I don't necessarily have time. But I added two references if you want to take a look at it. And so yeah, we can see that the parallelepipeds succeed in fitting well to the curve here of the anon map. If we look a bit how this area looks like, so on the abscissa you have the number of subdivisions. For example, here, if I take 20 subdivisions, it means that I have in total 80 boxes or 80 parallelepipeds. And in ordinate, you have the area of the approximation. So it's the sum of the area of each box or each parallelepiped. And as we can see, we have a better result. And it seems like we are converging faster than the natural and the centered evaluations. So we wanted a bit to know, well, if we were effectively converging faster. So if we take a look at the convergence, say that, so if I note epsilon, the width of a subdivision, of an input interval, if our area noted A converges in epsilon as a power n, it means that if epsilon, as epsilon approaches to 0, the log of my area will look more and more like a line, and the slope of this line will be n, the order of convergence. If we plot this for the three methods, so the natural and the centered and the evaluation and the parallelepipeds, you have the figure here. In blue and orange, you see the natural and centered evaluation. We have a slope of 1, meaning that it converges in epsilon. And in green, we have a slope of 2. So it seems like our parallelepiped inclusion converges in epsilon square. We still have to prove that, but this result is telling us that it should be converging in epsilon square. So here we had an easy case, let's say, because we add the expression of the function. For the unknown map, we have an analytic expression of the function. Now, what I need for my application is I have an ODE here, and the function that I'm trying to study is the flow function, the solution of this ODE. To do so, for my parallelepipeds, I need two things. I need to be able to evaluate my function, and I also need to be able to evaluate its Jacobian. To do so, I will rely on the variational equation here. So if I denote here A, the Jacobian of my flow function, it satisfies A dot equals the derivative of gamma for x and times A. This means that if I take this whole ODE here, this, let's say, augmented ODE, and I integrate this ODE over time t, it will output both psi of t and the Jacobian of psi of t. And to do this integration, as we want to have guaranteed results, I will be using the CIPD library for guaranteed integration. So an example here in 2 dimensions first, with the pendulum. So here we have the equation of the pendulum with here a term of friction and a small offset because my circle is centered in 0, 0, and nothing much happens at 0, 0 for the pendulum. So it's a small then I'm able to compute the derivative of this gamma function, so the equation of the pendulum. And with these two informations and the augmented ODE here, I'm able to integrate this and to get the flow function and this derivative. Sorry, so it's Jacobian. So this is the result that I get for an integration over 5 seconds. So the initial set is here on the left, so it's a unit circle, and I integrate it. So this is for CAPD alone, and so I have a total of 20 boxes. And this here is the same result, but with parallelepipeds instead. And we see that we are indeed smaller. We have a boundary that is smaller. Once again, if we take a look at the area of the approximation, depending on the number of subdivision, we see that we seem to converge in epsilon square, we converge faster. So this is after the 5 seconds of integration, meaning that these areas correspond to the last here, the last set. So this works in 2 dimensions, but as you saw earlier, the parallelipipedic inclusion function and that we gave is n-dimensional, so it doesn't depend on the dimension. So we can also use it in 3 dimensions if we want. So here I just showed a bit how the parallelepiped inflation would work in 3 dimensions. So in 2D, I had a line and I transformed it into a 2D parallelepiped. And here I have a 2D parallelepiped. And when I inflate it, I get a 3D parallelepiped here in green. Once again, I will use CAPD for the integration. I will use the example of the Lorentz system here. Once again, I can compute its Jacobian, and I integrate the augmented ODE, sorry, with this system. And so this is the result after 0.1 second of integration with CAPD alone. And this is the result that I get with my parallelepipeds here. And so we see that our result, as I said earlier, is we fit better to the curve because boxes, the wrapping effect of boxes in 3 dimensions can be an issue. And the main advantage of this method is that, as you can see here, this is a view from inside of the image set that you have here. Well, we are able still to determine the inside and the outside of the image set, meaning that we preserve the topology of the image set. And going back to our convergent character, if we take a look at the log of the volume, depending on the log of epsilon, we see that when epsilon gets small enough, we find again this slope of 2, meaning once again that our parallelepipedic inclusion, even when the function is not known and even in 3 dimensions, it always seems to converge in epsilon square. So once again, the proof is to be done, but this is telling us that maybe it should work. And so, yeah, as I said, the parallelepipedic inclusion is working in dimensions. We showed examples in both 2 and 3 dimensions. It seems to converge in epsilon square. We saw it twice, and yeah, it's still yet to prove. And for future work, we would like to study the ODE in the form of x dot equals gamma of x and u with an input to get closer to the reachability analysis. And finally, we may need, if we do this reachability analysis, we may need to be able to project our enclosure. So thank you for listening. And if you have any question, I'm available.
So many thanks, Maël, for your very interesting presentation. And yeah, as you just mentioned, you will now be available for answering questions. Who wants to start? Okay, maybe let me start with the first question. What you made as an initial assumption is that you are relying on the representation with the help of parallelepipeds, in which your m was smaller than the dimension of your function n.
Yeah.
Uh, this is something you could easily remove if you are replacing parallelepipeds, for example, by sonotopes. Is there any reason for this restriction that you have introduced, or could you easily generalize everything that you have presented today also to sonotopic enclosures?
Well, the result that we have here, maybe, I think it should be extendable to Xenotops, but we wanted to keep it to keep it simple, and so we limit our study to parallelepipeds.
Okay. So that means from your point of view, it's really just a matter of simplicity at the moment.
Yeah.
Yeah. And yeah, if I just continue concerning the reachability analysis with non-autonomous system models that you mentioned at the Outlook, how do you plan to parameterize the corresponding controls? Do you want to assume them to be piecewise constant? Because then I think it easily boils down to the autonomous case that you have just presented here. You would represent just the input as yeah, constant values, constant but uncertain, which can be embedded with the help of pure integrator models? Or do you also want to deal with time varying inputs for which you do not have any information about the variation rates? I think this could be something like external disturbances acting on the boat that you mentioned in the
Yeah.
beginning. How do you want to handle that question?
Well, the first step that I have in mind is a bit what I showed here, is to have a simple control, an open loop control, so it will be purely temporal. So here I'm using a Dobbins path, meaning I can only turn right, turn left, or go straight. And by doing so, if I have my robot at a given position initially, and I want it to reach a certain position, there is only one control going from this state to the position. And so before the mission, I'm able to say that the control will be this, and it's purely temporal. So this is the first step. It's not really about, we're not yet at the autonomous part because there is no sensor and no loop. It will be purely open loop, but I think it's a fair first step towards reachability.
But I think this is then just an augmentation of the state vector. You could represent this type of open loop control signal, for example, as the solution of another set of ODEs. You're just gluing them together.
Yeah,
And maybe you could even immediately apply your results to this kind of problem.
well, it should, but in this case, there is it's what I talked a bit about it in the conclusion. Then there is some notion of projection because I need to get my state. So yeah, this is, as I said, a first step towards reachability.
Mm,
But for now, I don't have a clear idea about how I could apply it really on reachability analysis. But I feel like it should be able, it should be doable.
mm. Yeah, very nice. Okay. Any further questions from the audience? I think everything you presented was perfectly clear.
Well, I hope so, at least.
Yeah. Then I have to thank you once again for your very nice presentation.
Thank
And
you.
yeah, I'm already advertising for the presentation that we'll have Friday next week. And yeah, our speaker for Friday next week is also present here in the audience. It will be Nedney Dialkov, uh, yeah, from Canada, currently being still in the UK, I think. Okay, then we are looking forward to seeing you, all of you, soon next week, and have a nice weekend.
Okay. Thank you.
Nice weekend.
Thank you. Bye.